We're anti-deriving. Another word for anti-deriving is what we call, does anyone know? Starts with I.
Inverse.
Not inverse. Good try though. This is integration, which is pretty much the same thing as anti-deriving. And therefore, in deriving, what did we do with the power? What happened to the power? Okay.
Brought it down.
Brought it down.
Just by
Correct. Anti-deriving, we are going to.
coefficient by
Yes.
so big grade by 7.
Correct. Okay. So the 6, instead of going down now, it goes up. Is a 7. And then we divided by the new power. However, that 3 is still there before. If I want to anti-derive, I want to start off, that's the original equation, but then we do this weird sort of line to signal to people that we're integrating or anti-deriving this. Okay? That's the first question. However, so if I go from here to here, if I derive it, if I'm working backwards from here to here, I'm going to get this. Okay? But there's something that we must consider. This equation, there are many ways to get to this 3x6. Because I could have 3x7 over 7 plus 1000. If I derive this, will I get back to this? Why? What happens to our constants when we derive them, when we go back? They disappear. So when we do antiderivatives, I could have 4. If I derive this, it will go back to this. So an integral, the integral of 3x6 has many possibilities because you can have so many different constants that disappear down back to the derivative. And so what we must do in order to get a general answer, you've got to put C at the end, which stands for constant. But that constant must be, they're all numbers. If I go over here, I'm going to integrate 2x minus 4. What is the new power going to be, Maya? If it's x to the power negative 4. Negative 3. Good. New power divided by the new power of negative 3. And whatever was there remains. And we must we must ensure that with the possibility that there's a constant that's going to be there. And that could be any number. Okay? Usually they would like you to give positive powers. So x to the power negative 3, Zach, where can I put that? 1/3. Not 1/3. Where can I bring this x negative power down? It's going to go down here to get a positive, and everything else pretty much remains the same. That negative can go to the front. Over here, dy dx. If I integrate a dy dx, so I'm practically integrating both sides. That's what we're really doing. For root x, what is the power, Gabe, of root x?
Half.
It's half. And then what we must do to help us integrate, we must bring it to the top. Okay? Have we done any integration so far? Any antiderivative on this? We haven't. We've changed the equation around. But don't make the mistake that you think you've anti-derived or integrated, because you haven't. Negative half. I need to add the power. Say negative half plus 1.
Like you're adding 1 to the power.
I'm adding 1 to the power.
It's just half.
It's just half. Okay. By the new power, what goes underneath, Manny?
4.
Not quite.
Oh, no, good.
You divide by the new power of half. The 4 is still there. But how many halves are in 4, Manny?
8.
There are 8. Which we can rewrite as 8 root x. And what are we forgetting, Perry? What do I have to add on to every single integral? The c. Okay. When you integrate a dy dx, we're anti-deriving dy dx. What does that churn out?
Y.
It's a y. Okay. It's a y. We're just saying we're going to fiddle around with this guy here. We're going to go up 1. The up 1 is a y. Any questions with that? Okay. We'll do a few more. Let's see if we can shorten this to not just one example. Let's see. Okay. So we want to find f of x. That's what we want. But how do I do that with an f dash x that's given? What do I need to do to the f dash x, Nathan? What's the action word that we're doing today? We're anti-deriving. And so I want to anti-derive my derivative. So once again, new notation, we're dealing with the f's. And the really correct notation is we put a dx at the end. That means that we are focusing all the x's. I simply substitute what I've got in here, 2x squared plus 3x. X squared, Jesse, x squared. What's if I integrate a 2, power 2, what does it become? 3. What's on the bottom? A 3. And what was already there? 2. Okay. Emily, what do I do with the 3x?
For the 2 on 2.
Okay. Tim, what do I need to put at the end of this?
I'm not sure.
That's okay. We'll put the constant in. Always put the constant in. Okay. Now, so we've got our general equation here. Okay, I want to find out what the constant is. How do I do that, Gabe?
You sub in f equals 0. Or x equals 0.
X equals 0 and f of x equals?
If x
You got the first part, yeah?
R1.
1. These two combine to make this notation here. we're saying that when I put an x equals 0 into our f of x, that f of x equals 1. So you've got two things to substitute into here. Okay? Manny, what am I going to change that to now?
The integration one, like the apostrophe.
Not quite. Not quite. We've got up here.
Oh, F1.
It's going to become 1. And Manny, what do all my x's now turn to?
1.
To 1s.
So it's just
0.
Zeros. My bad. 0, I thought so. Thank you. Okay, what's our C?
1.
1. So you rewrite it again, put a 1. Like so. Okay. What is that saying? This is a cubic. We're saying that it could be this cubic, it could be that cubic, it could be this cubic. But our 0 to 1, our 0, 1, which is right there, locks the general graph into this specific line. Does that make sense? You need a point to lock the integral graph exactly where it should be without all these variations of constants. Any questions? Okay, I'm not